welcome everyone. So glad everyone could come out, and thank you again for the Royal Tyrrell Museum Cooperating Society for supporting this. And our work takes place throughout the province as known as Alberta. We gratefully recognize and honor Indigenous peoples' long-standing connections to these lands. Today's speaker is Dr. Corinne Myers. Corey completed her master's in igneous petrology at Brown University in 2008, and then a PhD in paleobiology at the University of Kansas in 2013, and then did a NASA astrobiology postdoc fellowship at Harvard University from 2013 to 2015. She's been a faculty member at the University of New Mexico since 2015, specializing in paleobiogeography of marine invertebrates in North America. Her research focuses on species environmental interactions through time, including across mass extinction events and how those influence extinction vulnerability and selectivity. And today, she's going to be talking more about extinctions.
Thank you very much for the kind invitation. So my research started out actually thinking about biogeography of marine invertebrates in the Western Interior Seaway, which this land was covered by, so you're all familiar with it, I'm sure. But I also think about extinctions and do some kind of mathematical modeling, statistical modeling surrounding how the Earth and life have interacted to maybe support mass extinctions, and I'm going to talk to you about that today. This is a very sad scene from the PT, the end Permian mass extinction that killed off almost everything, and we'll go from there into how grateful I am to be alive and be working with all of these folks here. So this work, the data for this was mostly collected by a master's student of mine named Dustin Paraguay. And then we've redone these analyses many, many times. Most recently, my postdoc, Fernando Machado Stradell, helped us kind of work on that. And it's also been supported by lots of different funding agencies, including these two down here, which are work that I've been doing with some mathematical modelers. I am not a mathematician at all, so I'm the person in the room saying, no, you can't do that. The fossil record doesn't have that. But great ideas working with that partnership that supported some of this work. Okay, so we'll start out just sort of talking about biodiversity, talking about extinction for a quick minute. We'll go through the big five, and then I'll share with you this broad study that I've been kind of working on and reworking for several years. So we've had large, complex macrofaunal life since the Cambrian, which as of last year is now 539 million years ago instead of 540. That's a moving target. And what we know from the broad strokes of this fossil record is that we've increased not only in biodiversity, the number of species that we can count, but also disparity, which is differences in shapes, right? And speaking of aliens, if this doesn't look like an alien landscape to you, I mean, it really is almost an alien world back in the Cambrian. Okay, so biodiversity then is counting of things and their shapes, and it's controlled by two main levers, right? Origination or speciation makes biodiversity go up, and extinction makes biodiversity go down. So we're going to focus on that extinction part. This is now fairly old, but a nice just representation of what Phanerozoic biodiversity in the oceans looks like. So we have this early Cambrian, very large rise in biodiversity. There's the Great Ordovician biodiversification event. And throughout this, you can see these wiggles and waggles of biodiversity increasing and decreasing. And not just going up and down, but the steepness of the slopes is also very different. So sometimes the dips in biodiversity happen more slowly, right? And sometimes they're extremely rapid. Why is that, right? Why do these things happen this way? All right, so back in the 80s, Jack Sapkowski, who made that previous diagram with his cute little dog, and David Raup started thinking about this and compiled some of the first, this is a full-scale biodiversity compilation, and looked at then extinction rates through time and produced this plot, which is still relatively useful today. So they described two types of extinction from this. A background extinction, sort of maybe the slow extinction of species through time for whatever random processes are happening. And then things that are above that, right? So background using this data, and no one's really replicated this, so this is the number we have, is something like 2 to 5 families per million years are going extinct. If we translate that into species, we're looking at maybe 5 to 15% of species go extinct per million years over the Phanerozoic. Okay, but there are certainly intervals here that stand out way above this background level. And we have all been interested and continue to be interested in trying to figure out what causes those and why. So here's another plot that's showing essentially the same data set. On the y-axis, you're looking at the number of genera that go extinct. Genera are groups of species that are related by evolution. And because this is an older timeline, Cambrian, it should really be 539, but it says 542, and then here's modern over here. So the higher the blue line, then the more percent extinction is happening over that time. And we can basically look at these big blue peaks, we call them mass extinctions, and then we can give them a set of criteria. Now these criteria are extremely arm-wavy, and that is on purpose because the history of the Earth and its life is really complicated, and we haven't quite figured out if, what the sort of more stringent characteristics should be. So for a mass extinction to be called a mass extinction right now, we need to see about 70% or more of species that go extinct. They need to go extinct over a geologically short period of time, right? Because we've had long periods where species are turning over. That's not what we're thinking about here. That short period is typically less than 2 million years. Although the more we understand about some of these mass extinctions, that window is getting smaller and smaller. We're now thinking more on the scale of hundreds of thousands of years in many cases. Okay, it needs to be global. We can't just kill everything in North America. That's not a mass extinction. If we kill everything in North America and Africa and Asia, now we're moving into mass extinction territory. And it needs to affect a variety of habitats. All of the sort of compiled data I'm going to show you today are for marine animals and primarily populated by marine invertebrates. But to be a mass extinction, you also have to have significant extinction on land, mountains versus lowlands, deep sea versus shallow sea. All of those different habitats need to be affected. And then the recovery period needs to be substantial. And substantial typically means in the millions of years, maybe in the case of the end Cretaceous, it's faster than millions of years. But in some cases, like the end Permian, it's 5 to 10 million years before things start to actually recover. Okay, so we're going to go over the big 5, just as a sort of survey of these large extinction events. The first of the big 5 is the end Ordovician mass extinction that killed off somewhere between 80 and 85% of all species. We think this was triggered by a rapid glaciation that killed off all the warm-loving things, followed by a rapid deglaciation, which then killed off all of the new cold-loving things. So a two-pulsed extinction event. Things like conodonts, these are the mouth parts of sort of lamprey-like fish. Things like trilobites and rugose corals, all were hit particularly hard by this extinction, although none of those groups went extinct entirely. Okay, the next one on our list is the end Devonian, about 360 million years ago. Somewhere between 70 and 75% of species are thought to have gone extinct at this time. Majorly hit were brachiopods, stromatoporoid, sponges. These are some really bizarre sponges that are no longer with us. Nautiloids, trilobites, armored fish like placoderms were also hit pretty hard by this. This extinction actually includes maybe 3, maybe 4 different extinction pulses over 30 million years, each one associated with black shales and probably a fair bit of ocean anoxia. This one continues to be somewhat enigmatic in terms of its trigger. It may be an LIP, which stands for Large Igneous Province, these volcanoes that erupt for hundreds of thousands to millions of years. But it also may be related to the fact that during the Devonian, we moved a ton of plants onto land. That changed the weathering structure of the Earth system and then the buffering capacity of the ocean. immensely and forever, right? That was a threshold event where we changed the Earth system forever, so that may also have contributed to this, this extinction. Okay, the Great Dying, or the day the Earth almost died, is the end Permian mass extinction. That's about 250 million years ago, where anywhere from 90 to 97% of species are thought to have gone extinct. This one is most definitely triggered by the emplacement of a large igneous province. Here's my nice little picture of volcanic terror land. That one is called the Siberian Traps. Particularly hard hit here, Eurypterids go away forever, trilobites go away forever, fenestrate bryozoans, these net-like, kind of like corals but a little different, bryozoans, tabulate corals. We lose many, many, many different groups forever. Okay. This was closely followed, unfortunately, only about 50 million years later by the end Triassic mass extinction. This is also pretty convincingly caused by a large igneous province, which is called the CAMP event, the Central Atlantic Magmatic Province. We killed a lot of terrestrial reptiles. Ammonites did really badly, or ammonoids, I should say. Brachiopods, conodonts go extinct forever. Calcitic sponges were particularly hard hit. Anywhere from 75 to 80% of species went extinct at this one. And then the final mass extinction in the Phanerozoic that we have defined so far, and the one that I know and love since I work in the Cretaceous, is the end Cretaceous mass extinction. This one is quite convincingly caused by a large asteroid impact that hit the side of the Yucatan Peninsula, killed off so many things in North America in particular, but also initiated this global extinction. My favorite bivalves, the rudists, go extinct. My other favorite taxon, the ammonites, go extinct forever. Dinosaurs, of course, go extinct. And we used to have oceans with very large marine lizards that were very scary and toothy, and they also went extinct, never to return. I really like this one. I study it quite a lot. Okay, so you can sort of think of background versus mass extinction as something like, oh, ichthyosaurs died. We lost a species of ichthyosaurs. Versus, oh my God, the world is ending, in a mass extinction sense. I mean, if you really think about 70% of species or more going extinct, that means the rest of life is constrained to that 30%. And with the end Permian, you're constraining it to 5% of what remained, right? So that's a very interesting bottleneck. Okay. So great, but what we really want to know is, how does this happen? Because it is extremely destructive, and we probably would like to avoid it happening in the future, especially when we are around. I love this plot. It's from a Bond and Graspy paper in 2017, and what this is showing you is time on the x-axis, so 539 million years ago on the left, today on the right. This bottom panel is generic extinction. So higher bars mean higher generic extinction. And then up here, you get an estimate of the volume of lava that's being erupted by large igneous provinces. So if we're thinking about causal mechanisms and whether these lips are involved, this should give us an idea of what that is. The stars are asteroid impacts. So before 1980, we did not know that asteroid impacts could be so terribly destructive. But with the Alvarez paper, the iridium spike, all of the sort of evidence that goes into suggesting that this was quite a large asteroid and quite profound when it hit, we jumped on the bandwagon of mass extinctions are always triggered by asteroids. And for quite some time, it was a rush to find as many craters as you can and see if that was correlated with all of the extinctions. As you can see here, there's a crater around the Devonian, around the PT, and around the KPG. These two are actually just off a little bit in their timing, and so unlikely to have been the primary trigger there. But nevertheless, there are some large asteroid impacts in our history close by. Okay, more recently, the mass extinction causal mechanisms community has been thinking a lot about these large igneous provinces because very clearly one of the two largest, right, the end Permian, the end Triassic, were absolutely correlated and probably triggered by the environmental fallout of these large igneous provinces. So I've put large volume eruptions down here on the bottom, which is just the same as here. But when you look at this diagram, Oh yeah, here's the big 5 mass extinctions overlaid, just to get a sense for where those are. Okay, so when you look at this diagram, there are some problems, right? So there are these areas in the Cretaceous where you have potentially very large volumes of large igneous province erupted material, but there is not a mass extinction that's happening here. We have other times where we have some high extinction rates, but we don't really have an asteroid or a large igneous province to blame, right? So it's more complicated than just, was there a large volcano? Was there an asteroid impact? Okay, so this brings me to one of my soapboxes, which is thinking about extinction mechanisms both from the trigger perspective and the thing that kills you perspective. So my postdoc advisor, Andy Knoll, defined these in 2007 as essentially the trigger is the thing that is creating Earth system conditions that kill you. The kill mechanism is the thing that actually kills you. So kill mechanisms have a direct effect on your physiology as an individual, population, species. You will die, right? Things like ocean anoxia. No oxygen, you're going to die. Ocean acidification. I can't make my clamshell, I'm going to die. The temperature is too high, the temperature is too low, I've been eaten, right? These are all direct physiological impacts on an individual that causes death. Triggers then are the things that are creating those conditions globally, right? So these are things like your asteroid impacts, your volcanic eruptions, or any kind of major ecological change, like the evolution of predation, for example, was a very strong trigger early in the Phanerozoic. Okay, so I like to think of these geologically as proximal, close to you causes versus distal, far away from you types of causes. And because I like this subject so much, we're going to have a very small audience quiz here since I've described these. All right, so we have 5 hypotheses for how the dinosaurs went extinct from various internet sources, and we're going to decide whether these hypotheses are actually talking about kill mechanisms or triggers. So let's start up here. Gary Larson tells me that dinosaurs went extinct because they smoked too much. Is that a trigger or a kill mechanism? Why kill? But is it the cigarettes that are killing you? It's lung cancer. So I would call that a trigger, right? It's not the cigarettes. It's the fact that smoking the cigarettes gives you lung cancer. All right, how about this one? Gary Larson also tells me the dinosaurs went extinct because they were very smug about climate getting colder and animals having fur that might protect them. So cold, dying from being cold, trigger or kill mechanism? I hear kill mechanism. Why? Yeah, so you're literally dying from freezing to death, right? So kill mechanism for me, absolutely. Okay, how about this one? Not Gary Larson now. Someone else suggests that dinosaurs went extinct because they missed the boat. Trigger or kill mechanism? Trigger, why? Yeah, what kills them? Drowning, right? All right, died by drowning, not by loss of boat. Trigger, all right. How about dinosaurs went extinct because of dinosaur voodoo? Trigger or kill mechanism? Yeah, I call it a kill mechanism because the voodoo directly kills you, right? Even if there's some sort of dull intermediary. Okay, how about this one? Dinosaurs went extinct because mammals firebombed their boat. How rude. I heard both. Why is it both? Yes. So I originally was like, oh, this is a trigger. You die by drowning. And then my students were like, what if you get hit with the fireball? All right. Then it's a kill mechanism. Okay, good. We're all on the same page. So in that vein, we can think about recurring kill mechanisms that are almost always associated with elevated rates of extinction. And I like to call these the 4 horsemen of the evolutionary apocalypse. So the first one is temperature change. Particularly increases in temperature seem to be associated with larger rates of extinction. Another one is any kind of acidification of the global water system. So ocean acidification that makes it hard for me to grow my shell, or even acid rain, which makes it hard for plants to stay alive and do their business. Anoxia. This is actually one of the most black and white of all of the kill mechanisms. You cannot handle a little anoxia, even if you can handle a little acid rain. No oxygen, you don't breathe, you are dead. Okay, and that is limited to the marine realm. And then this is a new one that we've been thinking about in the last several decades as we look at current biodiversity crises and where or what may be causing decreases in population size and species health. Habitat loss. So whether you lose habitat, you're restricted to a smaller area, whether that habitat gets fragmented into lots of little patches, or whether that habitat gets degraded in some way. In a modern sense, we're thinking like pollution. In the geologic record sense, we're thinking more like, the vegetation structure changes and I have nothing to eat. Or I get excess nutrients in my marine environment and there's toxic algal blooms and I die. So thinking about these kill mechanisms and how they may or may not be associated with mass extinction events, we can also think about our mass extinctions in terms of whether there's some kind of threshold effect. So this idea, thinking about kill mechanisms this way, is supported in part by the fact that there's very few of these kill mechanisms that are always sort of present. The conditions of these kill mechanisms on the Earth is quite variable through time and not always associated with a mass extinction event. So this gets us to a question of, how do you define mass extinction events? Are they just the same processes but ramped up? So the thing that kills me is always anoxia, and I go from having anoxia in one area to having anoxia in a very large area. Is that correct? Or is there no continuity of cause in mass extinctions? It's a brand new thing. I've never seen it before. Boom. Another thing to think about when we're trying to associate these kill mechanisms with mass extinctions is whether they show continuity of effect. And what that basically means is that the same things die in the same conditions during background extinction as they would during a mass extinction. So the selectivity, the species that are most vulnerable to extinction are the same during background extinction, just more of them die in a mass extinction. And there's some evidence to say that yes, this is true. This one is a game that we're still playing. And the last one, this is the one that folks have focused on actually the most, is continuity of magnitude. So do you just have a slow ramping up of background levels of extinction and then we just say, there, that's the mass extinction place? Or is there a break there, right? Do you have background extinction of varying types and then mass extinctions are way up here and it is a totally different phenomenon, okay? And there is some evidence to say that maybe the end Ordovician, the end Permian, and the KPG are unique events that do not follow this continuity of magnitude hypothesis. The one I want to focus on is this continuity of cause. And I want to think of that in terms of how these kill mechanisms may exist on the Earth's surface to create threshold regimes where if you surpass the threshold, you go into a mass extinction time. So what does it mean then to cross a threshold? So this is a really nice system diagram by Dan Rothman and friends where time is increasing, going down. I'm not sure why he did that. And here you have a particular state of your system, right? This ball sits in this nice little well, and if we increase the temperature, it might roll a little this way, and if we increase the temperature, it might roll a little that way. But as long as we don't increase it very much, it's going to be able to go back to this equilibrium state. If you force it out of this well, it's going to fall into a new sort of steady state equilibrium place, maybe a temperature that is higher, and now it is hard to get out of that new well. You have to actually change the Earth system quite a bit to get back to this previous stability place. Okay, so we can think of these as almost like a state change where you're tipping out of this stable place in the Earth system and you're ending up in this new stable place in the Earth system. And that may not sound too bad, and it may not be. However, you don't know what that new stable place is going to be like exactly. The Earth is a very complex place. So we can think about it in modern terms. You may have an area that gets a certain amount of temperature or a certain amount of precipitation with a particular temperature regime, and it's a grassland, right? If you raise the temperature, reduce the precipitation substantially enough, you can cross a threshold and you can throw this area into more of a shrubland. At this point, you could start raining a lot, but it's not going to pick you or put you back into a grassland without a lot of change over a long time period. And maybe that's fine. Maybe going from a grassland to a shrubland is no big deal to you, but maybe that is a big deal to things that eat grasses in that area, right? Okay, so the way I'm thinking about this, the new regime is not moving from a grassland to a shrubland. Instead, I'm thinking about we're moving from a background extinction place to a mass extinction place. So in particular, we're interested in something called R-tipping, right? So we're tipping, and what R-tipping means is that it is rate dependent, okay? So you can have, so then you have a situation where your ball is kind of following the changes. It's not moving too fast, right? And so you can sort of stay in that stable well. But if the Earth system changes are happening very quickly, then your ball, your habitat doesn't have time to catch up, and you can end up actually being chucked down into a new place, which could be mass extinction territory. So if mass extinctions are related to R-tipping phenomenon, we would expect that there is a rate dependence on the kill mechanisms ramping up that tip you into that regime. So there's some evidence that the Earth system behaves this way. This is a really complicated diagram, but all I want you to see is that this is time. This is the timeline over which these different Earth system changes happen. So plate tectonics is happening over really long time periods. Weathering is over here. Land ice sheets are over here. And if you look at this diagram of how these different conditions change through time, we might think that R-tipping is happening in places where the slope is changing in this diagram quite a lot. So you have maybe some R-tipping right there, maybe some R-tipping right here. Okay, Dan Rothman then sort of took this, started thinking about the carbon cycle, which is potentially a really important part of mass extinction dynamics and Earth system change. And he did some math to essentially calculate how fast and how much of a big change in the carbon cycle may be associated with different levels of extinction. So all of these dots here are different types of extinction. The red ones are the big 5 mass extinctions. And these delta 13C, this is a stable isotope of carbon, and it reflects how much organic carbon is actually being buried versus existing in the Earth system. So it can tell us something about the carbon cycle and how it might be changing. So what Dan determined is that if we look at this amount of carbon change versus the timeline over which that happens, he could draw a really nice, pretty line here and say, look, most of the mass extinctions exist in a place where the amount of carbon cycle change is faster than this rate, right? So you have higher magnitude per duration in most of these mass extinctions compared to these intervals that are not mass extinctions. And he defined this critical rate as 0.23, doesn't even matter. That's just the slope of the line. Okay, so this suggests that maybe there is some kind of R-tipping behavior, rate-induced tipping, threshold crossing, when we move into mass extinctions, when we think about the Earth system that is supporting those mass extinctions. So I started then to think about how this might be reflected in other parts of the Earth system. So we know that large igneous provinces and asteroid impacts and other large and rapid changes in climate are related to mass extinctions. So what does it mean then to think about what the world was like before those changes started, right? Does it matter whether the plates were all together as a single Pangean supercontinent and you had these changes in the Earth system? Does it matter if your climate regime started out warm before you moved into this mass extinction phenomenon? So this brought me to the hypothesis of whether the background Earth system conditions, so the way the Earth system is before a mass extinction, might act to make that Earth system more vulnerable to extinction should you trigger it with one of these different ways, okay? And if there is an enhancement of how the Earth system is oriented leading into a mass extinction, then can we use this information to think about the future, right? How vulnerable are we to this type of elevated extinction? So we test this by looking for a relationship between these pre-existing conditions, how the Earth system was organized environmentally prior to a mass extinction event, and then connecting those to magnitudes of Phanerozoic extinction. So I pulled extinction magnitude or extinction rate data from 3 different sources. The first is the original Sapkowski curve. That's the curve that I showed you earlier, which shows a general trend of big increase in diversity over time, kind of this stable plateau. The PT really reduces biodiversity, and then we have almost exponential increase in biodiversity through time. I also pulled extinction rate data from a John Elroy and friends compilation, which uses a method of sample standardizing to try to make each time bin more equal to the others and fill in time bins that are missing fossil data. So if you have any biases associated with a lack of fossils, or you just couldn't get to sample those fossils, these methods of sample standardization should make all time bins a little bit more equal. So they're better compared. And they find something very different. Instead of this trend of increase, plateau, increase, we have wiggles and waggles that kind of never reach above this particular timeline. And then added in another sample standardized extinction data set from Mike Foote that he published in 2023. So this is what these data sets look like. Again, you're looking at the amount of extinction, on the y-axis, and then time on the x-axis. And all I want you to see here is that there is a difference between sample standardized methods and non-sample standardized methods, which we would expect. The Sapkowski data set identifies 18 elevated extinction events. Elroy finds 16, and then the Foote data finds 18 as well. So these data sets are a little different, but that's actually why I used all of them, to see if there's consistency across different modes of calculating. So I paired that with environmental data for the whole Phanerozoic from these authors. And that environmental data includes stable isotopes of carbon and oxygen. So oxygen we can think about as a proxy for temperature under the best circumstances. When the 18O value is lower, it's hotter. When it's higher, it's colder. So I collected average temperature from this, and then also the standard deviation tells me something about how variable that temperature might be over a timeline. Then I took the delta 13C, that carbon cycle proxy, and I looked at the standard deviation of that as a proxy for how stable is the carbon cycle. Is it very unstable or not very stable? Strontium isotopes here tell you something about weathering. I have a sea level curve that tells me something about the amount of habitat that's available or how fast that habitat is changing, so standard deviation. This epsilon hafnium proxy is telling you something about the amount of tectonic activity on the Earth. And then there's a very nice data set from Miller looking at an estimate of percent atmospheric oxygen through time, so how oxygenated is the atmosphere compared to today. So this is just an example of what these data sets looked like before I compiled them. When I compiled them, they look something like this. And you can see that they are trended, right? This is decreasing through time, decreasing through time. You have broad trends here. I don't want my comparison to include these trends. I want to know just in a base way how these are related to my data. So I detrended them using something called less regression. And so now my data looks like this. It basically, well, we could talk about the details of that if you'd like to, but it's a pretty easy mathematical transformation. You just end up with data that no longer has those big trends. Awesome. If there's outliers, so points that are way out here, we removed them, 3 standard deviations and larger. And then, because I don't know how to think about this, we've not thought about this before, I binned these proxies into 3 different time bins to estimate this relationship with extinction. So we binned 2 million years of them together, 5 million years of them together, 10 million years of them together, to see if if this timeline had anything to do with the relationship of the response. To look at the comparison between extinction and the changes in these environmental variables, we used a very simple method of multiple linear regression, which just tries to fit essentially a plane or whatever dimensions you have to your data points, okay? And we used this one because the system, the data themselves are extremely complicated. The Earth system is extremely complicated. So we don't want to add additional methodological complication, we want to use the simplest way possible to try to see through some of that complicated history into any kind of broad patterns. Adjusted R squared is going to tell me how good the model fit is connecting extinction rates to these different environmental parameters. We adjust this for having lots of different variables, lots of those different environmental variables, and all you need to know is that if the R squared is above 0.2 for a complex system, that's not so bad. We use two different statistical methods to look at model selection and how good the model is fitting to the data. One of them is this AIC, the other one is a Bayesian method, and they essentially tell you the same story. So when I show you results in a second, you're just going to see the AIC-based models. Yay, it's nice when different ways of doing models end up with the same answer. That makes you feel good. All right, so summary. I have 16 to 18 extinction events that I'm connecting to these different environmental parameters that I'm binning over 2 million, 5 million, and 10 million years. And then, because I have 3 different ways of estimating extinction, 3 different ways to bin time, I end up with 9 best models, 3 times 3. All right, here's the results. I know this is very sad. No one likes to look at graphs, so we're going to go through just the important parts. The thing to note, so these are all the best models. I can't tell you if one is exactly better than the other, except by the criteria we're going to go over right now. But if you're looking at that first data set over 10 million years, this is the best model that was produced by this analysis. So the first thing to note is that in all 9 models, the standard deviation of delta 13C, that carbon cycle instability proxy, is important. In 8 of the 9 models, mean delta 18O, or mean temperature, is also very important. Okay, the highest R squared of these models is in the 2 million year time bin. That tells me that that is probably a better timeline to be considering these relationships than something that's much longer. And because this original data set does not correct for sampling biases, we're just going to go ahead and say that it is unlikely to be as accurate as the others. We're going to asteroid it out. To tell which of these last 2 might be better, we look at the size of the model coefficients. When the model writes an equation, this is how it works. It has coefficients, and the coefficients of this LRA model are a bit higher than they are in the foot model. So we're going to kind of barely asteroid that guy and focus the rest of the talk on just this LRA model over 2 million years. And this is what it looks like for the different factors. So we could call this the best-ish best model. This is the model. Extinction rate is related to 18O, standard deviation of 18O, 13C, and a little bit of strontium. But the only variables that have significant contribution to the model are this mean temperature and carbon cycle instability variables. So we're going to focus on those. This is called a predictor effect plot. So you're looking at the impact. Oh, you can't see the bounds. That's okay. You're looking at the influence of these different variables individually. If you could see the 95% confidence intervals, you would see that these lines, you could draw a horizontal line through that confidence interval for these 2 bottom ones, which are strontium and the standard deviation of oxygen. The standard deviation of carbon and the mean of oxygen, you cannot. Okay, so that means that these 2 variables, you cannot distinguish a relationship between that's not random, whereas you can with these. So we focus on those. So the interpretation then is the following. So this is extinction rate versus oxygen. So hotter is more negative over here, colder is more positive. And what we see is that there are higher extinction rates when it is hotter. Similarly, this is our carbon instability plot, where you have less stability on the left side, more stability on the right side. Less stability on the right side and more stability on the left side because of the standard deviation. So extinctions are high when you have a larger standard deviation, more variability in the carbon cycle. So beyond enhancing extinctions, is it possible that this lead up to an extinction period is actually causing the extinction? Is mean temperature being high or carbon cycle instability being high actually causing the extinction in any way? And if that were true, what we would expect is that your variation would get higher as you get closer to the extinction. So these are 2 million year bins right before, 2 to 4 million years, 4 to 6, all the way up to 8 to 10. So farther away, less stability, closer, farther away, more stability, closer, less stability would be my expectation if this factor may be controlling extinction rate. Same thing with temperature. Closer in, I would expect temperature to be hotter. Farther away, I would expect it to be lower. When we look at the actual data, though, it looks nothing like that. So this is carbon cycle, this is oxygen. There is no trend in these variables as you go closer to the extinction event, which suggests that that they are likely making it easier to have a higher level mass extinction. They're not actually causing that mass extinction. Okay, so if we feel fairly good about this Alroy model, what does that tell us about the future? So what you're looking at now are the Phanerozoic extremes. So the late Pliocene has the lowest extinction rate of all of these events. The Permian has the highest. And then the rest of the big five are nestled in orange there. If we look at our modern extinction prediction from this model, it's right here and right here, which essentially amounts to about an extinction rate of 0.6. And that's a bit smaller than our two lowest of the big five, so which had about 75% extinction. So we're looking at a prediction of 65 to 70% if we were to trigger an extinction today. So that's very useful. What do we do? What do we do with that information? So if it seems like there are these thresholds, then we need to start thinking about what is the tipping point, right? We are vulnerable, based on this analysis, to an extinction being worse than it would otherwise be if we end up tipping into a global mass extinction. And what that requires really is for us to think hard about how to scale ecological processes, or the breakdown of ecosystems, to geological processes, global level Earth system and extinction. This is some new work that is about to be submitted to, I can't remember where, in the next couple of days. But what I'm showing you here is a vulnerability metric, which is considering diversity, standardized speciation, and extinction. So where vulnerability is above 0, 0 is about right here, you are more vulnerable as a biosphere, and where it's below 0, you are less vulnerable. And what we can look at, and this is now temperature versus vulnerability, is that over the Phanerozoic, there seems to be a pretty significant relationship between temperature and vulnerability. Higher temperature means a more vulnerable biosphere. And beyond that, you can see that these transitions between different climate megastates, which was the other part of this project, we can divide the Earth into the Phanerozoic into these 5 megastates. The transitions are associated with large extinction events. So, what do we take away from this? That thinking about the world before we move into a mass extinction regime is potentially really important, right? Carbon cycle instability, higher mean temperatures going into a triggered mass extinction event mean that mass extinction event is going to be worse. They don't cause that mass extinction, they just make it worse if it's triggered by something else. The data suggests that 2 million years of our past history means we're in a vulnerable place. If we were to trigger a mass extinction, for example, by human activities or other global climate change, that extinction is likely to be worse than it would have been otherwise. And if what this means is that we're approaching a transition in our megaclimate states, that we're even more at risk. Okay, and finally, I want to leave you with study the fossil record, because it's a 539 million year experimental record of how species have responded to the Earth and all of the Earth's changes. And so it can really tell us some important things about how life and environments interact that we can use to inform conservation biology today. Okay, and that's all I got. Thank you. Yeah. Happy to answer all questions.
How you made a comment that rather than maybe 2 million years as a critical time period for some of the mass extinctions, it might have been closer to several 100,000 years or so. There was the same type of question, I think, for the Cretaceous extinction. I think this Tyrrell did a lot of work on that. I can't remember any of the numbers, but I think there was hundreds of thousands of years before the mass extinction during that critical period. How confident can you be going back to, say, the Permian? How can you even get that kind of resolution in time? Do you have that sort of resolution in the fossil record? Can you rely on it?
That's a great question. And it is actually the reason that we didn't just use the full extinction record and instead picked just these elevated intervals, because the elevated intervals have been extremely well studied. And so at the end of the Permian, especially because that was such a terrible one, people have done huge amounts of global proxy measurements, global finding fossils and documenting diversity before, leading into, and after the end Permian. So these events have the best data. I did, and I could show this slide if we feel like it, I did do this analysis across the whole Phanerozoic time series without cherry picking the elevated extinction events. The results don't change too much. That carbon cycle instability and mean temperature seem to be important predictors of extinction risk. And I'm also doing another study thinking about conditions during the extinction, and the same thing is coming out there too, that having higher temperatures and having more carbon cycle wackiness make the biosphere very vulnerable. So, so I think, does that answer your broad question about the data, how we collect the data before and after? Yeah.
How close can you get and how long it took for that to occur?
Good point. Okay, so the resolution of these data sets close to extinction boundaries is in the hundreds of thousands of years, sometimes tens of thousands of years. If you allow for geophysical modeling and let them kind of take these data and try to interpolate to smaller timescales, for the KPG for existence, for example, we can get, we're talking now about recovery of from the KPG in terms of years, but that's a very unique situation. How many years? Just years, like. So I study the KPG. I have the most expertise with that mass extinction, and the latest geophysical models that are coming out of UT Austin and in conjunction with this guy who studies forams named Chris Lowry, you're looking at temperature being very, very cold after the asteroid impact hit for 2 years, maybe 3, for darkness to have lasted only about 3 to 5 years before it starts getting lighter again, and the climate is coming back online to what it was similar to before by 20 to 30 years. Years, yeah, not thousands. But that's extremely unique, right? We do not have that kind of resolution for any other event besides that one. Yeah, go ahead.
Sorry to take up more of your time, but that sounds hauntingly similar to the situation of the last Ice Age termination event, which some scientists have been saying. I haven't followed it for 5 or 6 years, but it was within perhaps 3 years and maybe much less than a year, possibly. So finding that at a geological scale in terms of going back to the Cambrian sounds a little hard to actually pick out, but I mean, there are people suspecting it's there.
Yeah, it is hard to pick out. The farther back you go in time, the fewer the rocks are, and the worse the temporal resolution tends to be. And that's where, besides the KPG and maybe the Pleistocene, the resolution is tens of thousands of years for the PT as an example, and maybe the TJ also. But then by the time you get back to like the Ordovician and the Cambrian, you're talking hundreds of thousands of years is the resolution, which is within the 2 million year bin that we're using. But we could try 1 million and see if it's better, or breaking it up beyond 1 million. I'm not sure I would trust the data is particularly accurate.
In one of the first graphs you showed there with all the extinctions and singling out the 5 main mass extinctions, there's also 2 increases within the Cambrian. I was wondering what factors of the extinctions you pointed out, those ones are missing.
I love it. That's a great question. So I can't go back and show you, but there were several, maybe 3, large extinction events that happened early in the Cambrian. And the question is, what's up with that? I didn't talk about those as being particularly large. So those were included in the analysis. There is some question about their how accurate they are, because the record gets so sparse back then. So you end up with very few rocks. If you have very few rocks, then if you see a big dip in biodiversity, is that because you don't have very many rocks, or because there was a big extinction event there? So you start questioning, to some extent, the quality of that record as you go farther back. From my experience, I think it's worth including them, so I did. It's replicated in all of these different data sets, even the ones that are trying to sample standardize for things like the amount of rocks. So I included them in the analysis I was showing you, but there are folks who are like, well, you can't know that back there. There's just not enough information, right? It's sort of like if you have 10 things and you take away 5, then that's a 50% extinction. If you have like 1 million things and you take away 5, we're not even talking about it, right? So it's kind of this law of numbers in terms of what the record looks like. For the temperature and carbon cycle record, what is the significance and R-squared value? It was in the 0.66 to 0.7 range, I think. But we'd have to go back for the exact number. Oh yeah, here, great, thank you. Okay, so the R-squared for the model is 0.6 and 0.86, and then the coefficients are telling you about the contribution, which was 0.39 and 1.14 here, and 0.37 and 0.62 here. I don't remember the exact R-squared values for each of those variable contributions, but the higher coefficients suggest that it's more important for the model, and it was statistically significant at a 0.05 level. I think it's actually significant at 0.005 level. I didn't include that there. Even if we successfully battle climate change in the decades ahead, is there any real possibility of stepping back for the species that are currently on the verge of disappearing? That's a great question. I think it is extremely species specific, which if I had to give you a theme for my entire career as a scientist, it is that so far there's a lot of specificity in how particular species handle particular Earth system changes. So I think it depends. Are things like polar bears and tigers, do we have a potential, snow leopards, right? Condors, do we have a potential to sort of, keep them around? Yeah, probably. But the amount of the highest number of species that are going extinct are plants, and part of that is we don't study them enough to really know how they work. So I think it's going to be very taxon or species specific whether they can or cannot be saved. And I hate to say that I'm a long-term thinker as a geologist and paleontologist. I'm thinking in terms of like hundreds of thousands to millions of years. So part of me is like, these are not going to make it, but many things might. So let's focus on those as opposed to sort of focusing on the ones that are right on the cusp. If we, it's almost like the last slide, right? What if we make the world better for no reason? Like we've still made the world better, right? So we may save some of these species just by, trying to do the best we can to keep the Earth system where it's at, right? Because at the end of the day, the equilibrium that we're in right now works for us. So if we move into a new equilibrium and that equilibrium happens to be hotter and maybe species, including us, are more vulnerable to extinction at that place, there's all kinds of unknowns that are difficult for us to sort of predict, right? But if we stay where we're at, we kind of have a good sense for where we're at. So, a lot of me is like, let's just try to preserve this right here that we know works, as opposed to entering into this threshold crossing type regime.
So your previous answer leads up to my question.
Oh, good.
I've always been amazed that ammonites bounced back from several mass extinctions, and yet they got clobbered at the end Cretaceous. Oh. Do you have an idea of why that
breaks my heart? I have an idea of why, but I don't know that I find it very satisfactory. So I love ammonites. They're my favorite of the fossil taxa that I work with. There are sort of two ideas that have been thrown out with some decent support in the last several decades. One is that they were range restricted. So there's a strong correlation in lots of different things, that if you have a larger geographic range, it's much harder to make you go extinct. And that's in part because if I drop an asteroid on here and you're over there, and here, right, you're much more likely to survive than the thing that's only where the asteroid is. Having a larger range also suggests that you can probably deal with a broader range of environments. You eat more types of food, right? So that might also help you survive. So ammonites have smaller ranges overall than something like a nautilus, which was at that time very global. So one hypothesis is that ammonites were just too specialized in their ecology and also in their geographic range, and so they were more susceptible to extinction than something like a nautilus. The other hypothesis is about larval development. So nautiloids will kick their eggs into the water, and they have food in their little egg sacs, and they can float around for a little bit. Not a real long time, but for a little bit. And ammonites really don't. And this is where I've never actually seen an egg, so I don't know how they estimate this, but it seems like their larval development may mean that they had more direct development, that they kind of didn't have that ability to float around and maybe weather some of the bad stuff they had to hatch. And if you hatch in bad conditions, you're not going to survive. So that's sort of the two main hypotheses. I don't find either one particularly, it doesn't satisfy me fully because, like you said, they survived the PT, for goodness sake. But they did get highly, bizarrely specialized in the late Cretaceous. That's when you start seeing them uncoil. You had, straight ones. You had ones that looked like uncoiling ice cream cones. You had ones that looked like dog poop that I don't even know how they swam. So it may be that specialization, that small geographic range, was the thing that just made them not successful. Some of my colleagues recently just published a paper, and this is only slightly relevant, but it's cool, so I'm going to tell you anyway. So some of my colleagues just published a paper about surviving ammonites, and so there is evidence in Europe that you had ammonites surviving for the first, tens of thousands of years after the extinction. Probably just extremely low numbers. Sites that I have visited in the Gulf Coastal Plain of Mississippi, we have what very well may be some surviving ammonites there as well. So they may have made it across, but they probably made it across in such small numbers that those populations couldn't be sustained, and they just eventually went extinct. Kind of like a living dead situation. Alive, but not reproductively capable. Yeah, isn't that sad?
All right, thank you very much.
Thank you.